louder.
Okay.
Hello, everyone. I have the great pleasure of introducing Professor Daniel Katz. He's a chief scientist at Network Center for Supercomputing Applications. And I think it's very important to us to have him here to present research software, to understand what's the importance of research software for us scientists that rely on software for almost everything. So Daniel, thanks, please.
Okay, thank you. Yeah, so thanks for the invitation. It's nice to be here. I want to talk about why research software is important and what we can do to better support it. Just to start off, I can talk about why research software is important, some of the reasons, some of the evidence. I think that software is essential for the bulk of research today, for the majority of research today. And we can look at this in terms of a few different things. We can look at this in terms of funding, where we can see that in the US, about 20% of projects funded by the National Science Foundation over an 11-year period topically discuss software. 2 of the 3 main areas of the Department of Energy US exascale computing program really are research software programs, another $4 billion US. And at the National Institutes of Health, there's about $300 million of work that includes software development. And so we can also look at publications. We can see that software-intensive projects are a majority of current publications, and that the most cited papers today are either methods papers or software papers. And you can think of software usually as an implementation of a method. Researchers, we can also ask. And we can find out that if we ask 2 different studies of US and UK researchers, we found that about 90% use research software, about 65% wouldn't be able to do their research without it, and about 50% develop software as part of their research. So I hope that's reasonably convincing that software is important in research today. If we think about where software fits in the cycle of research, the idea that is taught in school is that you create a hypothesis. You often then in practice have to acquire resources to investigate your hypothesis, and those resources could include funding, they could include software, they could include data. You then actually do your research, and in the process of your research you may be building more software or creating more data. You publish your results, which could be a paper or a book, or it could be the software itself, or the data itself could be the results. And that's the knowledge that comes out of the project. You then want to continue the cycle. You want to create a new hypothesis based on the results that you've come up with. And in order to do that, you need to actually get recognition for your results. And that recognition then will help you the next time acquire the resources, acquire the funding, maybe find collaborators in software, collaborators in data. So software then shows up as part of the research itself, and it also shows up as what I'll call infrastructure. It's the thing that is not being developed in the project, but the things that you're starting with and the things that you are producing, the things that are being shared. So if I think about this a little bit more, we can say that some research software is intended just for the developer's own research. It's intended for immediate use. It can be small. It can be something like a script, for example. It's funded by a lot of different funding agencies. It's often funded implicitly, that you don't say that you're going to build software as part of your proposal, but everybody knows that that's part of the project is going to be to build some software. And it can be archived for future use and for reproducibility. And it's almost certainly going to be dependent on research infrastructure software. Right? You're not creating all the software you need. You're going to depend on some other software as well. So the other research software then is intended as infrastructure. It's intended to be shared. It's funded by some agencies, not as many. It's almost always explicit. Right? You say that you're going to produce this software for a community to use. You're going to produce this compiler because you want people to use it. It's intended for use by that community over a long period. It's not just during the project. It's intended to last beyond the project. And it's easier to be appreciated and rewarded for this software effort because people are using it, because it's being shared. So this is going to be the focus of the rest of this talk. I'm going to try to focus on this research software. Sorry for the boxes. There may be a few minor issues where things don't quite line up. I'm presenting on a computer that's not the same as the one that I created the slides on. So we can take the software that's intended for research and we can turn it into this research infrastructure software. But to do this, you have to make a conscious choice, and you have to realize that this has both positive and negative consequences. So we can think about how projects change. We have a project that starts, let's say, in it's a fluid phase, but this could be when you're thinking about your own research and building your software initially. And then you get to, eventually, ideally, you get to this kind of specific phase at the end when the software is infrastructure. And the idea is of this chart is that at the beginning, you're really working on the software itself. But by the end, you're really working on how you're going to deliver the software and how people are going to use the software and how people are going to interact with the software. And much less on the software itself, much more on the community. So if you're going to go through this, at each point, you or the developer has to think about the methods to do this and the goals of doing this and the consequences of doing this. Choices that you have to, or questions that you might think about are what resources are available to help in this transition? What kind of work is going to be needed? Do you have the skills to do the work with the community, for example? Are those skills available? What are the incentives for doing this? Do you have will you be promoted in your career? Will you be recognized for sharing your software, or would it be better for you to write more papers? How will your success be measured? Again, is this something that your institution, your university cares about? And will they support it as well? So not only do they care about it, but maybe they have some staff that can help you with this, or there's somebody with some specialized skill that can be brought in to help. So I've been talking about research software without actually defining it, so let me define it at this point. I'm going to use a definition that's from Grunpeter. And it is that research software includes source code files, algorithms, scripts, and computational workflows and executables. So a lot of different types of software that were created during the research process or for a research purpose. That's the research part. There also is additional software. There are additional software pieces that you'll be using. Operating systems, libraries, dependencies, packages, scripts, other things that are used for research, but weren't created with a research intent. And so we are calling those software in research and not research software. And this may vary between disciplines. So for example, if you're a computer science professor and you're building a compiler, that compiler for you is probably research software. But if you're a chemistry researcher and you're using a compiler, that compiler then for you is software in research. It's not part of your research. It's not something that you particularly care about, even though it's something that you need. So the other thing that's worth mentioning about research software and software overall is that software can collapse. It stops working eventually if it's not actively maintained. The structure of computational science stacks, often you can think of as 4 different layers. At the bottom, there is a non-scientific infrastructure that is usually developed by somebody who's not a researcher. This is things like the operating system and the compilers and the support code. On top of this is the scientific infrastructure, which sometimes is developed by researchers, things like libraries and utilities that are used for research in a lot of different disciplines. On top of this then is discipline-specific software, often developed by researchers. And this is things like tools or libraries that implement disciplinary methods and models. In addition, then, on top of all of this is project-specific software. And this is the software that actually is used to do a specific research project. It's the building blocks from the lower levels that are being used, and they're being orchestrated in some way. Scripts or workflows or notebooks or special purpose libraries and utilities that make the project work. And the key idea is that the software that's on the top builds and depends on the software and all the layers below it. And so any change that happens in a lower layer can cause the software on the top to collapse. Right? If the operating system changes, if the compiler changes, if the library changes, any of those things can be a problem. And so in order to avoid software collapse, somebody has to be actively working at the top and looking at any of those changes happening on the bottom and trying to adapt to them. So here we have research software, again defined as the software that's developed and used for the purpose of research to generate, process, analyze results within a scholarly process. It's increasingly essential in the research process, but there's a bunch of problems, and those include the fact that it will collapse if it's not maintained. This can be because software bugs are found, new features are needed, or new platforms arise. And again, these platforms can be hardware platforms or software platforms. Software development and maintenance is very human intensive. We don't know how to automate this. Software that we're talking about here is often developed specifically for research by researchers. And those researchers know their disciplines, but they don't always know software best practices. The researchers are not rewarded for software development and maintenance in academia. Again, I apologize for the slight overlap as the format of the slides has changed. And the developers also don't match the diversity of overall society or of the user communities. So there's a number of different problems that we can think about trying to address here. To go into some examples of these problems, one that's interesting to look at is the OpenSSL issue that happened about 8 years ago now. So in 1998, there was a UK group that built OpenSSL as a very common internet encryption tool today. In 2011, a bug was introduced into this library. By 2014, 2/3 of all websites were relying on this library to run the website, to make the website work. At the time, there was one full-time developer, Stephen Henson, who was kind of supported by a software foundation that was a private for-profit company. In 2014, this bug was discovered. The bug was fixed fairly quickly. It wasn't a complicated bug. It was just a bug that was hidden. And the OpenSSL Software Foundation requested donations in order to support the developer so they wouldn't have this problem in the future. And out of the 2/3 of all websites in the world, a total of $9,000 was given in donations. And they then led a much larger campaign trying to really publicize this issue, and they ended up getting support for 4 developers for 3 years initially. And today, OpenSSL is a very active project that has about 19 committers. It has financial and in-kind support, including staff time from a bunch of companies. And it's a healthy community with good governance. So this showed a problem. This problem was successfully addressed, and things are now in a better state because the role of the software was shown to be important, and people decided to invest in something that they thought was important. Another problem is something called the bus factor, and the bus factor is kind of a maybe not so polite term, but it's the idea that if you have people that are working on a project and some of them are hit by a bus, can the project continue? And the bus factor is how many of them would need to be hit by this bus for the project to not be able to continue. So if you have a bus factor of 1, the project is depending on one person entirely. If you have a project of 10, that's probably pretty good, a bus factor of 10. So NumFocus is an umbrella nonprofit that has been built to support scientific software, and it's supporting all these different groups that are on the right that include Julia, Jupyter, SciPy, Matplotlib, a bunch of things that probably a lot of people use in day-to-day research work. NumFocus has had a sustainability summit more or less annually since 2017. And in 2017, they did a survey of the bus factor of these projects. And they found that about half of them had a factor of 1 or 2, and the other half were more like 4 to 6. So these 1 to 2 projects are basically relying on one person not to be hit by a bus, or also not to retire, or not to change interests, or something else in order to keep, again, these projects that are very widely used projects going. One project told an interesting story where they talked about having developer support, but also having a huge backlog in the number of open issues that they couldn't work through, and having some students coming on to help, but the students weren't actually able to deal with the open issues because they couldn't make decisions for the project very easily. In the wider open source community, one survey that was done in I think this was 2017 or 2018 as well, was looking at 2/3 of popular projects on GitHub and finding that there was really only 1 or 2 people in those 2/3 of those projects that were the main committer or the main maintainer. Another problem was faculty recognition. So I had a young faculty member came up to me and talked to me, somebody who is very involved in open source and open science and reproducibility, and if I said their name, probably a number of you would recognize them. They had a pre-promotion meeting with their chair where they were told that the committee wouldn't count the software efforts and the software papers that they had been working on because these were not traditional journal papers. And they were told that being visible and being recognized for open science and reproducibility was okay, but this wasn't really what they were going to be counted on. And having an official H-index that was high was the important thing. And theirs was not high enough because they were putting their energy into these other things. And it's worth noting that this institution was not a signatory of DORA, the San Francisco Declaration on Research Assessment, which says specifically not to do these things. And this institution, which is a major US university, still is not a signatory of this. And in fact, very few US universities are, which is kind of interesting. I think here, this is probably the other way around, where more universities, I think, have actually signed. Whether or not universities that sign actually live up to it is a different question. There was a nice story in maybe 2019 where one of the universities that signed this had then put out a job ad saying that they were looking for people with very high H indexes, which was something that they weren't supposed to do having signed this. So there's always challenges. The last thing, I want to just give a series of tweets. Again, this is from 2017. A user of Pandas, a large data library, said that in a public statement, a public tweet, that the documentation wasn't good, and they gave an example of a problem with the documentation. And one of the people on the project said, if you're not happy with the documentation, please submit some patches, make it better. All right, we're not getting paid to write documentation for you. And then somebody else said, well, you're the chief data scientist of this company. Shouldn't you be putting some of your team's time into helping to contribute to this open source project? And somebody else said, well, he probably could, but he probably isn't going to, because people look at open source software and they think of it as, you're giving me software for free, and in return I'm going to use it and I'll complain about it. And so this is a problem. We don't really have good expectations about open source software at this point. So it's worth going back now to Max Blanc for a minute, who said this, and I don't know how many of you speak German, but I don't, and so the answer in English, sorry, I guess I should have done this in Portuguese as well, is that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that's familiar with it. And the way that this often gets translated or shortened is that science advances one funeral at a time. I actually just saw this on a Mastodon post this morning, and so this is kind of a common phrase. But my version of this is more that the culture of science advances one funeral at a time, right? Because it's the people that are the current practitioners that cause their culture to be the one that's accepted. And when they move away, let's say we could say retire, again, to be more generous, then people that have newer ideas then have space to explore those ideas and to try to convince other people that those ideas are right. So, so having said that, then what do we actually do? So I think what we're trying to do then is to think about software sustainability in particular. And software sustainability in brief means that the software endures. Will the software continue to be available in the future on new platforms meeting new needs? You can only measure this in hindsight. You can't actually say a software package is going to be sustained. You can just say that a software package has been sustained. But you can make predictions about it based on what you see about the software environment and the team. Again, the software development and maintenance requires active human effort. Human effort, sorry, I've lost a bunch of symbols in my slides as well. So this is intended to say human effort does not equal dollars, does not equal money. We have projects where we have entirely human effort, like community open source projects, and those have been proven to work for a long time. We have projects that are all based on salary, and those also have been proven to work. Commercial software, grant-funded projects, right? Both of these models work well. The challenge is when you try to put these together. That's interesting, my symbol worked in that one. Effort does not equal money. People are not purely rational. So if you have a project where some people are getting paid to work on it and then you ask other people to volunteer, that's a kind of a tricky thing to do, because they say, well, why should I volunteer when you're getting paid? So there's a little bit of a challenge here. And this is really, I would say, one of the big challenges with a lot of projects is how to resolve this issue. So to define research software sustainability then in a slightly longer term, I would say it's the process of developing and maintaining software that continues to meet its purpose over time, which includes that the software adds new capabilities as needed by its users, responds to bugs and other problems that are discovered, and it's ported to work with new versions of the underlying layers, including both software as well as hardware. So there's a few different ways then that we can approach this. One of them is that we can try to reduce the amount of work that's needed to sustain the software. Another is that we can try to bring in new resources to do the work. And the third is that we can do both, that we can try to reduce the work as well as increase the amount of resources. And we can do these at different levels and by different groups. So an individual project can do things to reduce the amount of work or to bring in new resources. A community can do this. A funder can do this, or an institution can do this. And by institution here, I mean primarily hiring institutions, which could be universities or laboratories or companies or someone else. So on the first of these, to think about how to reduce the amount of work that's needed, one of the best things that we can do is to train developers, which means we have to find and develop training material to begin with. And then we have to figure out who needs to be trained in this. The Carpentries is probably one of the best organizations that's doing kind of the basic level of this, of trying to develop generic material, to make it discipline specific, to make it language specific, and to teach it to students and to postdocs and other people in universities who are not in computer science but are in a wide range of other areas where they also need to do some software development. We can also do things about best practices, right? Because as I said before, most researchers don't really know software best practices. And so that means we have to first find or develop these best practices. Again, Software Carpentry is an organization that's doing this, and incubators as well. ESIP is an earth science organization. Apache is a computer science foundation. Both of these have incubators that try to work with projects to instill best practices for the maintainers of those projects. It's also important to include research software engineers in research teams. And I'm going to talk about what research software engineers are a little bit. Actually, I'll do that now and with a few details. So if we think about where research software comes from, as I've said before, a significant fraction of it is developed in research. When computing started, software really appeared around 1948 or so is the kind of where I see software starting to be called out. Research software started pretty soon after that, and in particular in weather in the early 1950s. And software engineering started, I think, in the late 1960s, or at least it started being called that in the late 1960s. And it was mostly applied to operational software at that point, things like the operating system on a computer, on a shared computer, a NASA flight, things like that. I also mentioned before that researchers, and think of faculty in particular, and students as well, generally don't know good software practices. That's not their expertise. And software engineers, who we have lots of today, generally don't understand research. Right? They understand production software engineering. And then we also have students and postdocs who both don't know good software practices and also aren't going to stay with a project for a long time. They're going to go somewhere else when they graduate or when they leave. Some postdocs do stay involved in projects. They often, sometimes they join the staff of a university. Sometimes this is unofficial. They may be called a postdoc for 10 or 20 years with just a variety of different short-term jobs. Staff who have research understanding and software engineering skills can be developed over time and do develop. So we can think about this in terms of kind of two alternating views of a craftsperson and a scholar. We can think of a scholar as being a researcher who's really driven to understand things to their fullest capability. They find intellectually demanding problems. They do work that's curiosity driven, and they work on a topic until that understanding has been acquired. and they pass this on through teaching or through writing a paper or writing a book saying, I understand this, this is how I can explain it. A craftsperson, on the other hand, wants to create things, wants to create artifacts. And they want to create things that really explain themselves and can be used in a kind of in a hands-on way. They're unhappy when things are fragile or ugly. They prefer to make things that explain themselves, and they do work that requires patience and pride in doing a job well. They typically are not driven by teaching. They're typically not driven by writing papers. Scientific software needs people who do both of these things, who understand things and build tools and pass on those tools. And so those are research software engineers to me. If we think of a space that has software engineering on one axis and research on the other axis, we can think about people who are software engineers who are really good at software engineering, not so good at research. We can think about people who are researchers who are really good at research and don't know any software engineering. We can think about people who are researcher developers, and this is actually growing to be more common. So people who are quite good at research and also have a decent understanding of software engineering and software development. But research software engineers are more really in the middle of this. They have better software engineering skills, and they also have better research skills than software engineers. And this is really kind of a fuzzy cloud. It's not a point. So there's kind of a wide range of research software engineers in here. All of these could be considered clouds in some sense. So then if we think about advantages of research software engineers, if you have a research software engineer, somebody like I described on the last slide on your team, this can lead to better software and more mature project management. It can lead to a better team organization, a better way of actually organizing work as well, a better way of organizing the software, better coding practices. Altogether, these lead to better, more sustainable code and more efficient group coordination. RSEs also provide institutional memory. As research software becomes more important and complex and costly, the expertise in it is valuable. Sometimes if you think about a software project and you think about a person that's been the key developer may be more valuable than the software project because they can recreate the software, but if you lose the person, the software may be hard to maintain. So RSEs often have longevity beyond an individual project and beyond a student, and they're also often mobile across domains. So if you have an RSE who's been working in applying force fields in computational chemistry, they may be able to take that skill and apply the computational part or the physics part or something else in a different area. And so they can take something that's happening in one area and translate it into another area. They also can build community expertise because if they're the expert in something, other people will come to them and a community starts to form around experts. So there's a lot of different resources that are available about research software engineers today. This idea was born in the UK. It was born in 2012, and late in 2013, the UK RSE Association formed, and it had about 50 members at that point. It's now a society that has actually almost 600 dues-paying members and about 3,600 people overall. There also are RSE organizations in Belgium, Germany, the Netherlands, the Nordic countries, and Australia, New Zealand, as well as a US community. Actually, we're up to almost 1,500 members now. There are also new associations now forming in Africa and in Asia. This is a map just showing places where there are RSE organizations in the darker red and places where there is the beginning of an RSE organization in the kind of pinkish color, the lighter color. And then the blue color is places where there are not formal RSE organizations yet. And you'll note that South America is blue. And so if there's anybody that's interested in this and would be interested in forming an RSE organization or starting to, there is a leaders organization within the different countries that crosses across the different countries. And so if somebody reaches out to me, I can put you in touch with people in the leaders organization who will give you guidance on things to do. And again, talking to the people in Africa and Asia that are kind of maybe a step ahead now is also another way to do this. These associations then work on local issues, and they can do this collectively, and they can also coordinate across different countries and different regions. And to do that, there's an international community that's formed that's under researchsoftware.org, And it's where every month or two we have a meeting of the different RSE organizations and we talk about should we have a conference together? Can we share information? Are there projects we can work on together? Things like that. Okay, so we're talking about the other piece of this then, not just reducing the work that needs to be done, but the second piece of increasing the available resources that can be used to sustain software. So one of the ways we can do this is to create incentives so that people want to work on the software, particularly people in the community. And one way to create an incentive is to use citations. And because people, at least in academia, are typically rewarded based on citation, at least in part, so we can think about what can we do with citations to help with existing faculty. Can we give them citations for the software work that they do, for example? And so let me go into that for a minute and talk about this. So I've been co-leading an effort to promote the idea of software citation for about 8 years now. In 2016, we produced a set of software citation principles. This was published in PeerJ Computer Science. Actually, I'll just mention in 3 hours, there's going to be a webinar on software citation and current work. And if anybody's interested, if you look under PeerJ Computer Science under Twitter or do a web search, you'll likely see this this webinar that's going to be in about 3 hours. We then looked at creating guidance for paper authors who want to cite software. We produced a checklist for that. We produced a checklist for software developers who want to make their own software citable. We created a document of best practices for software registries, for registries and repositories that want to store software. All right, what are the practices that they can use to encourage people to submit and to maintain the software as well as possible? And so this document was produced, and there's also a community that's going on now. And so if you're involved in any kind of a registry or repository and you want to think about putting in software in addition to data as one of the things you store, you can get in touch with this group in order to join and find out best practices and talk about questions. And then one of the things that we've been doing most recently has been working with publishers. And in 2021, we published a paper with a bunch of different publishers that provided generic guidelines for journals and for conferences to customize for their communities to say how people should cite software. And this is also now being tracked by Chorus, which is a group, kind of a publisher group, so that publishers can look and see what other publishers are doing in this area as well. Okay, so that was talking about citations that can help existing career paths. Another thing we can do is to adjust existing career paths so that they reward software work. And so this, I would say, I would call kind of promotion in an academic sense. And so let me go into some detail on this. I think the thing that's probably most important to realize is that promotion and evaluation are they're not fixed processes. Right? These were not created thousands of years ago, and they're just the way they are. They're created fairly recently, and we can change them. The guidelines for promotion and evaluation in academia in particular are important because they say what is valued by an institution, and they shape activities that people undertake. Right? If the institution says that public outreach is important, then you'll see people going out to schools and going out to museums and doing that because they know that that's part of what they're going to get graded on. Promotion guidelines were written by senior people, and so one question is, how do they actually get changed over time? But one thing that we can do is we can influence these processes when we participate in these evaluations. Right? So you may have a process that says you should count this. That doesn't mean you also can't count something else. Right? You just have to make an argument to other people on the committee to do that. We can also develop guidelines for recognizing software contributions and encourage our organizations to adopt them. So if you're involved in any kind of discussion where the promotion process is being discussed and it's going to be changed in some way to maybe, I don't know, emphasize open science, emphasize reproducibility, emphasize something else, you can use that as an opportunity to say, well, let's count things for software as well, for example. The National Academies in the US in 1994 put out a report that was called Academic Careers for Experimental Computer Scientists and Engineers. And this actually had, I would say, kind of two big impacts. And one of them was it said that experimental artifacts in computer science are important and they should be considered in the evaluation of computer scientists. This was intended to provide a reference point for change. And a lot of people, at least in the US, that write letters of recommendation for tenure will point to this report and say that this person is doing what the National Academies say, and this is important. It's happened slowly. The uptake of this has happened slowly, so it's not widespread, but I think people are starting to do this and have been for a while. One of the challenges is that this was focused on computer scientists. This was not focused on people in biomedicine, for example. So it's important to think about how do we do something like this in other fields as well. Another thing that happened in 2013, the National Science Foundation, which is the main funder of scientific research in the US, changed its requirement on biosketches, which is the thing that somebody puts in when they're applying for a grant. It used to say that you should put in five most relevant publications and 5 other important publications. And they changed the language from publications to products so that you could say not just what are my publications, but you could say here's the software that I've produced, or here's the data set that I've produced, or something else. And this was intended to be a signal to universities, at least in the US, that they should also consider other objects. And how well that's worked is a little bit of a question, but at least in some cases it has worked. Okay, so that's some things about promotion. Another thing is new career paths. And again, I'm going to talk about RSEs a little bit, research software engineers here. So research software engineers often have a mismatch between their time and their funding and their careers. They typically work on a series of grant-funded projects, which are short-term projects, maybe 2 years, maybe 5 years at the most. And often they cannot work full-time on a given project. They have to work on multiple projects because there's not enough money in the grant to hire a full-time RSE. And so these projects have shorter duration than staff careers. So this tends to lead to something that we call matrix management, where people are reporting to a principal investigator on a particular project, maybe on multiple projects, and this is changing over time depending on which projects are active and which they can be working on. But they also report to a group manager who doesn't change, and this is the person that's concerned about their career and their promotion and what they learn and how they develop over time. This idea of having RSE groups like this, where people are in a group but they work on different projects, builds this kind of idea of a pool of experts and expertise. It welcomes others with shared interests, and even outside of that group. But this then does have some challenges as well. And so one of the challenges is how do you actually fund the manager of this group, which could be done by overhead on the projects, it could be done by some kind of tax on the projects, or it could be done by the institution in some way, realizing that this is important and they should support it. You also have to worry about funding staff growth. So if somebody wants to go to a class or go to a conference and is not tied to a particular project, how do you do that? How does somebody explore a new technology? Maybe they want to see if they can learn Rust and try to understand if that could be used in some of their projects, or a new language or something else. And how do they actually get time to work on proposals? So these questions are all things that have to be answered and are answered differently for different universities. Just to give an example, RSEs at NCSA, where I work, NCSA is a research institute. It's hosted at a university, but it's not within any of the academic departments. It's in parallel with the departments and the colleges. The RSE team size is about 35 people at this point, with 2 levels of management. So there's groups that are about 5 people, and then there's somebody on top who's managing the groups as well. The charge, the remit for NCSA is to support individual project needs, and then to try to generalize those needs across projects, and to build software frameworks in response that come from a project, but then can be used for other projects and can be expanded to other kinds of work. Each project then that is coming in has a senior developer who's supported about 10% of their time, and their main job is to mentor the other staff in the project. And we also have a rule that RSEs generally work no more than 50% on one project. We don't want an RSE to be 100% on one project. We would rather have 2 50% people, which works both for if somebody goes on vacation, as well as just having that discussion and that collaboration so that people actually talk to each other. And we don't have a project that's owned by a person, but we have a project that works in ways that multiple people agree on. The funding model is that the staff are funded by research grants entirely. Management has the people at the top that are funded 50% by the institution, and the group leaders are funded 20% by the institution. So the rest of their time, they also work on projects. We think that we've done a fairly good job on job security and on career progression. Staff are on indefinite contracts. So there's some chance that somebody could be asked to leave at some point, but we haven't done that as far as I know. And we have 5 grades of research software engineers, from assistant to RSE to senior to lead to principal. So there's a path for promotion over time where people get better recognition and better salary. And I'm not going to talk about this in any detail, but I just wanted to point out, and I guess I should have said as well, the slides are at this DOI on the bottom, so you can look at this, you can look at any of the links yourself as well as the details. But we've kind of gone through a lot saying what are the skills that you need at each level, and who makes decisions, and what kind of supervision is there needed, and what kind of education and training do you need at each level, and what kind of experience should you have at each level. And so this gives us a map to say when is somebody ready to be promoted, or if somebody new is coming in, what level should they come in at. Okay, so that's new career paths. The other thing that we can do, or another thing we can do to increase available resources, is to try to make the role of software and research clear to research funders, and then make the case for them to increase both funding for new software and to provide funding for software maintenance. I would say actually here, you're kind of in a good situation. FAPESP seems to be on board with this and seems to realize both of these things are important, and seems to be creating new ideas now about how to fund some of these things. So this is, I would say this is an area where Sao Paulo is leading, well, at least co-leading and maybe leading the world. You can also think about seeking institutional resources. So if the software is considered sufficiently important to the institution, right, it's something that the institution either makes its reputation on, or it is important in projects, maybe the institution should be putting in some resources as well. Maybe they should be supporting, I don't know, a quarter person to keep working on the software to maintain it for the institution. Okay. I also mentioned that you can do both of these things. You can try to reduce work and bring in new resources at the same time. And so the primary way to do this is to encourage collaboration. If you can use the work of others rather than re-implementing a function or a package, that reduces what the software team and its developers need to do. And in addition to that, those collaborators may also contribute to the software and can reduce this even further. If others are using a team software and they contribute to maintaining it, then you have less that you need to do. But in order to make this work, the software has to be designed from the beginning to be modular and reusable, which is often hard because you're thinking just about your own use case. It's hard to think about other people's use cases as well at that initial time. And it also has to be very clearly documented and explained to potential users, even those that are in different fields than the developers. And then the other piece is that you have to then make the software findable and accessible and interoperable and reusable. And this is what FAIR stands for. And FAIR has had a lot of take-up in data, but it's had less in software. But FAIR, the ideas of FAIR apply to software as much as they apply to data. And if you can make your software fair and engage the community, then that's a way of getting people to find out about it and hopefully to start using it and maybe to contribute to it. So let me provide some details on FAIR for a minute. For about 2 years, we've had an effort on FAIR for research software. The idea here is that the FAIR principles at a high level are intended to apply to all research objects. But in text, the principles often say metadata with meta in parentheses, and this is shorthand for metadata and data. So even though this is intended to apply to software, it doesn't actually say software, and this is a little bit of a challenge. Software can be stored as data, but it's not just data. In particular, software is executable while data isn't. Data really is providing evidence while software is providing a tool. Software is a creative work where scientific data are typically facts or observations. They have different licensing and copyright practices, at least in the US and in many other countries as well, based on these differences. Software has the kind of bit rot that data has, where the bits maybe are going to be hard to read in the future, but it also has software collapse, which is something that data doesn't have an issue with. The lifetime of software is generally not as long as that of data, but it can be reasonably long. And one of the big issues is that for open source software, there's not the same processes that you have for data, which were baked into the FAIR principles. So the FAIR principles have this idea that you create a data set and you then transfer it to a repository, and that repository then maintains it and shares it. And in the process of doing that transfer, you define a bunch of metadata, who are the authors, what terms could be used for searching, things like that. For software, if we think about open source software in GitHub, we don't have that model at all. Right? People can use the software as soon as it's on GitHub without knowing who the authors are. It can be very hard to search for. There's no process, there's no time at which it becomes public in many cases, unless people have taken a private repository and made it public. But if you're working in the open from the beginning, right, there's no step between the creator and the publisher. Both of these things are happening simultaneously. Every time you're changing the software, the publisher knows about it. You don't have to go through some kind of large process in order to declare it. Okay, so in the FAIR for Research software work, what we decided was that these high-level goals, again, findable, accessible, interoperable, and reusable, are mostly the same, but the details of what they are and how they're actually implemented in practice depend on how the objects are created and used, how and where the objects are stored and shared, and how and where metadata is stored and indexed. And again, these are all very different for software than they are for data. So we did a bunch of work to define a set of principles, FAIR for Research software. And we had about 500 participants overall that were involved in this process, leading to this set of principles that was published earlier this year. And it was done under these three different organizations: Force 11, RDA, and RISA. Force 11's focusing on scholarship and publishing, RDA focusing on data, and RISA focusing on software. So we wanted to bring these all together for this purpose. There's now work underway to implement and adopt these principles. Okay, so that's a little bit about FAIR for Research software. The other thing then is that you also need to put effort into engaging and working with the user and contributor community. And so let me just talk very briefly about engagement. If the goal is to engage people in software, we think about why do volunteers or collaborators choose to put effort into our project, and how can we engage them? I'm going to say that engagement is intrinsic motivation plus extrinsic motivation plus support minus friction. Intrinsic motivation, the things that are inside, the reasons that you do something; extrinsic, that you're doing something based on external rewards, external feedback. Support is that it's easy to do something effectively, and friction in some ways is that it's hard to do something, that there's something that prevents you from doing it. We can think then about a bunch of different things that projects can do. Right? They can use GitHub, for example, for development. That reduces friction because other people know that technology and can easily use it. They don't have to learn something new. They can provide templates for issues and guidelines for good pull requests. And because we're running a little short on time, I'm not going to go through kind of all the reasons here, but I'm just going to kind of do the highlights. They can provide a code of conduct and have a welcoming and encouraging environment to bring more people in. They can provide good first issues, things that new people can work on that will help, again, bring them into the project. They can make sure that when somebody contributes, they get added to a list of authors that are cited when the software is used, so they get some reward when the software is used. They can highlight examples of how the software is used, because it's been shown that people want to do things that they think are important to the world or important to science, and they don't want to do things that they think aren't actually going to have any impact. And they can ensure that the project is diverse and to highlight diverse elements within the project. So if you have a group that's not traditionally been involved in software and they don't see people that are like them in a project, it's less likely that they're going to join. But if they do see those people, they can use them as role models, and that may encourage them to join. So a project also can think about engagement progressions. They can think about people coming in, discovering the project, having first contact, participating, maybe eventually moving up to leadership. And at each point, there are things that you can do to encourage somebody to come to that point and to move from one level to another. And again, in the interest of time, I'm not going to go through this, but again, the slides are at this DOI and you can look at this. Communities also have things that they can do. In particular, communities can look for systemic change that they can make. They can support incentives and citation through their processes, through their conferences, through their publications, things like that. They can support RSEs. make sure that RSEs are seen as a valid career path and are recognized within meetings of the community. They can support software work, like having prizes that they award for best software, most impactful software, having conference sessions where people can come together and talk about software issues. They can encourage fair software. They can communicate about the community, about software, about needs, and about gaps. They can collaborate, so they can develop and maintain community software projects. Funders can do things as well. Again, systematic change is something that funders can do. Supporting incentives and citation again. Supporting RSEs. For funders, they can consider funding fellowships and training for RSEs. They can make sure that when they provide funding for software projects, that funding allows RSEs to be part of those teams. It's sufficiently large. And they can even put into guidelines that projects that include software engineers will be scored more highly or things like that. They can encourage institutions to hire and support RSEs as well. They can fund more explicit software development, including a path to open and generalize and sharing software that's developed in research projects. So if they funded a project and that project has done something interesting in software, maybe they should create a path that software could be shared more widely outside of just that project, right? Some additional funding that could be added to supplement, perhaps. Funders can require fair software. Funders can require open software by default. Right, maybe with some exceptions, because sometimes software shouldn't all be open, but most of the time it probably should. They can require projects to talk about sustainability of the software. There's something called software management plans that are starting to come out, kind of like data management plans. These are not widespread now, but they're probably a good idea. And funders can also accept that if they fund new software, that implies that somebody is going to have to keep maintaining it over time. And that probably is going to involve more funding. And then finally, they can also support research in measuring the impact of these changes and improving these changes. So we don't, as I said at the beginning, I gave some little numbers about the impact of software and how funders are funding software, but we don't really have very good data, and we don't know if it's increasing or decreasing over time because it's really hard to get information from the funders that we can use. Yeah, and so that's that. And then what institutions can do, like USP, for example, think about systematic changes again, supporting incentives and citation, and again in promotion and hiring, things like that. Hire RSEs, provide an RSE career path. Think about if there's an RSE group that would make sense, or building a community among RSEs that probably exist in a bunch of different faculty labs where they could at least come together and talk. Count and reward software work, again, in hiring and promotion. Support fair software. Support software management plans via templates or tools or services. If there's potentially, if there's a data management organization at the university, if there's a library at the organization that's concerned about data, they should also think about software. Support key packages as institutional products. Encourage open software in general. Potentially by creating an open source program office. This is something that started happening in maybe 5 universities around the world that I know of. And the open source program office is a place that somebody can go and learn about open source software. Maybe find out what license they should use for something, find out if the university has a policy that they need to follow or that can be changed. And then finally, and this maybe is more of a US issue, is to ensure that technology transfer offices are measured on transferring technology. In the US, at least, technology transfer offices often feel like they should be measured on bringing in income, on selling things, and not on actually transferring things. And often it's more important to transfer the technology than to try to figure out if they can make money from the technology. Okay, so with that, I'll wrap up. Just to point out, there's a lot of different people that have been involved in a lot of these different pieces. A few different people that have been involved in the software citation work. People I've talked to about RSEs over probably almost 10 years now. People that have been involved in the Fair for Research software work. Other people that I've talked to more generally about how universities work, how funders work. A project called Better Scientific Software that gave me a fellowship at one point to pursue some of the citation work. And if you're interested, I have a blog that I write on occasionally, and I've been starting to use Mastodon quite a lot, and I've kind of stopped using Twitter, but you can choose which of those to use. So thank you, and I'll be happy to answer any questions.
Thank you, Daniel. repeat the questions.
Okay,
So
I will do that.
I will start with here for the live
Yeah,
edition.
yep.
But I have an additional question. So you're aware that Katz is supporting this kind of ways of maintaining software. So when we have a grant, we can have up to 10% of the grants to support software. Do you have any additional hint or other than giving money, what should they also support or provide?
So I think one of the challenges is that often the need for support of the software happens after the grant has ended. So one question, sorry, I should repeat your question. So the university here has permits 10% of the grant funding to be used for supporting software. So what else could be done? I think, is that okay. All right, so one thing is, again, that the need for the maintenance of the software and the support of the software often happens after the grant. And so some way of kind of taking the money and shifting it in time would actually be something that I think would be useful. In the US, when a grant comes in, there's some overhead that is charged on the grant by the university, and that pays for the building, the facilities, the power, or other things. Some small portion of that goes to the department or the college, and sometimes in some universities, some of it goes to the PI as well. And once it gets to the university, it's no longer tied to the grant. It's different in time, and then whoever has that funding can use it in whatever allowable way they want to. And so again, I think a question would be, could some of this money be put into some kind of an account where it could be used then to support the software later? I think the other thing I would say really is it's the kind of the big piece is this idea of research software engineers. And so what can the university do to support research software engineers? Can it create an organization for them to talk informally? Can it, first, can it help people understand that maybe they are research software engineers, that that's really what they're doing, they just didn't know that was the name of it. And then maybe they can be thought of as having some group, right? With any kind of a service at a university or any other organization, there's always a tension between having it being very distributed and having it being centralized. All right, so for example, an HPC system, you'd want to have centralized. You wouldn't want to have, 10 different faculty members each having very small HPC systems in their labs. You would much rather have one larger system that's being shared. All right, so you can think about the same thing for research software engineers. Is that a model that makes sense to have people who maybe are postdocs in a bunch of different laboratories, or should they be brought together in a way that they can learn from each other and the laboratory isn't dependent on just that one person, but they can use the services of the 10 people or the 20 people? So I think those would be a few things that could be done.
We have one question. Is there any research software sustainability conceptual model, framework, or guidelines published for research and developers to follow?
Yeah, so is there a research software sustainability conceptual model, framework, or something else that's published for researchers and research software engineers to follow? I think the answer is not exactly. There's been a lot of publication over the last, I would say, 5 years, 4 or 5 years in work in this area, and there's a lot of interesting papers to read. There's a lot of discussion about what important topics are. There's some discussion about what particular projects have done that are successful, but I don't think there's something that's gone as far as that question in terms of really bringing all of it together into a conceptual model, or even going even further and turning it into specific guidelines. So I think that's probably a next step that we need to think about.
We have another online question. There are several factors that can influence the success of research software and consequently its adoption by researchers. What is the big challenge for one of these software to achieve success?
Okay, so there's a bunch. So the question is that there's a bunch of factors that are related to if software actually gets adopted and used effectively, and what is one of the most important factors. Is that okay? Okay. I think I would say that maybe there's a few different things. One is just ease of use. Right? Is the software easy enough to use? Does it do enough general things? Another one is actually, is the software findable? Right? Do people use it? One, which seems like it happens based on collaborations, based on somebody publishes something and they say, I use this software, and then other people want to use that software as well. One way of looking at this is to look at the workflow system world, where there are, at least there's one wiki page that I know of that lists something like 340 different workflow systems that all basically are doing more or less the same thing with some differences, running a set of tasks on a set of resources in some automated way. Some of them are used in particular communities, like Galaxy is an example that's used in a lot of life sciences communities. There are others. There's one that I work on called Parcel, which is a parallel scripting library for Python that effectively does the same thing. So there's differences between these that are based on, like, do they have a command line interface versus a graphical interface? Are they built for tasks that are short versus tasks that are really long running? Are they do they work better on clouds or on HPC or on something else? So there are some differences, and there's probably reasons that we need to have some number of different packages, but we probably don't need 340 of them. And it seems like the way that people use these is based primarily on what their colleagues use. So it seems like one thing that really is important is having something that's being used and is being championed by somebody who has the ability to talk in public and has a good reputation. If you have somebody that's a champion for a particular package, that tends to lead to other people using it, and if it's a good package, then that will kind of continue to snowball or to spiral. The other thing that also happens is that I think the other big thing is outreach. So if you're developing a new package and you can work with a champion, but you can also go out and give tutorials on it, or have a Jupyter notebook that shows how to use it and have a bunch of good examples, that also will work. In particular, good examples I think are really important, because users often don't really care about your tool, right? They want to get their job done. And so if there's an example where they can just remove something that's in the example and plug in their piece, and that lets them do what they want, then they'll be pretty happy often. Okay, yes, question?
Thank you very much for the amazing presentation. And you mentioned the importance of training. And I'd like to know if do you have taken knowledge, some experience with software engineering graduation courses for researchers from other areas?
Yeah, so the question was about training and the importance of training, and if at Illinois we have training in software engineering for researchers from other areas. Is that? Yeah. Okay. And so the answer is the answer basically is both no and yes. So we don't have formal software engineering training for people in other areas because, as I was kind of saying, and I apologize to software engineers, the software engineering training and software engineering skills are generally not directly usable by people in research. They usually make different assumptions that don't seem to work for researchers. So one of the challenges is not taking kind of traditional software engineering education and applying it to researchers, but coming up with a customized version of software engineering training that works for researchers. And again, I would say that's what the Software Carpentries does. There's a project called Code Refinery that's in the Nordic countries that does this as well. The UK has a project called, I want to say Excalibur, that's trying to do this for HPC systems. I might be getting the name wrong, I'm sorry. There's a US project that's starting to do this as well, that Ian Cosden and Jeff Carver lead, and the name is escaping me for the second. So I think there's a bunch of different levels at which this is starting to happen. At Illinois, we offer software carpentry training at least twice a year, sometimes more often. And most of the people that come are not from computer science, they're from other areas. So that's the basic one that we offer. And we are not offering anything above the basic one now, but I think we're really interested in doing something that's at this next level. And that's this code refinery, for example, is a set of training at the next level. And I think we will do this in future years, but we haven't done it yet.
You have more. Go ahead.
Okay, this is one very good because this is how you can summarize your talk in one question. How do you make project leaders aware that they need to employ research software?
Okay, how do you make project leaders aware that they need to employ research software engineers? So I don't know that I can answer in general, but I can answer for what we do at Illinois. And it's that it's not necessarily, so the research software engineers themselves don't necessarily do this, but other people at the university, the manager of the group and the manager at a higher level do this, I think, quite well. And what they do is when there's a project going on that they find out about, they talk with the project leader about it, and they try to see what's going on and what are the problems. And then they'll explain how a research software engineer often could help address some of those problems. This is really hard to do with the project that's going on as it's going on. The impact is usually that the project leader learns this, and in the next project, they would come to us and they would say, all right, we're writing a proposal for this project. We think we should put in a research software engineer now. Can somebody in your team work with us on the proposal? And then if it's funded, can you work with us on the project? So I think that's usually what happens is we often find problems and we convince people that having an RSE would have solved that problem or would have avoided that problem. And then on the next project, the people are often convinced and they will do that.
Thank you.
Good to see you, Daniel. And of course, here in Sapa, rather than Shandana. And very nice talk, by the way. And I'm happy to see that some of this started happening. In fact, my affiliation with USP is related. I would call myself an RSC anyway, which I have been, besides doing real work in industry, but also collaborating with researchers for a long time. And in fact, when I was at Illinois with NCSA, I remember that there was this cool project where these physicists were trying to model the universe. And then we were able to get a collaboration project with the computer science department because they did some really cool software for Fortran, but then trying to, then once again, the good software engineering principles weren't being involved. So I'm happy to see that the people can also take credit, something that's evolving in the right direction rather than just pure publication. But what I'm thinking of, because recently I also did some work helping some people at the NREL, National Renewable Energy.
Yep.
And they're doing interesting research too with that, but I was helping them with the software engineering side of that as well. And a lot of people were in Colorado, but they're in other places as well. And one thing that, when we had a lot of this discussion, the maintenance, which you talked about, versus, because a lot of times you do experimental work. Even in industry, you're doing that. You're trying to innovate, you're trying to do something new. Same with the research environment. So it's sometimes it's a one-off. And so you wanted to go off and try something before you actually figure whether, so have you thought, when do you, so early on, it's too expensive to do all, even in industry, we try to push this 3x, you're exploring, then you expand if it takes off. And then you want to make sure that it can cost you a lot if you make a mistake at this level with kind of the S curve, the normal business S curve. But I wonder if you've thought about how that balances with, because in research it's the same thing. You're experimenting, but if it takes off and it has to live, that's when you really need to be concerned about software maintenance the best engineering practices, good testing, but that's too expensive to do early on, and even at the National Renewable Energy Laboratory, it's how it balanced.
Right. Okay, so let's see. So maybe a short version of this is that there's lots of experimentation with software that happens, and it's expensive to apply best practices at the beginning. So typically, but by the time that you get to something that's taken off, then you definitely do want to have those practices. And so how do you transition between those? Is that
Yeah.
okay?
That's good.
Okay. So I don't think that I really have a great answer for that, other than at the beginning of the talk, which actually maybe it was right before you came in.
Sorry.
No, that's okay. I was talking about the fact that there's lots of different software that gets developed in research, and it's part of a research project. And at some point, the developers or the leads have to decide: are they going to try to expand the use of this? Are they going to try to share it? Are they going to go through all those things? And so to me, that's the point at which that decision gets made. And unlike unlike the NREL case, it's not a decision that the answer has to be yes, right? So it could be something that that a professor thinks, this is a great idea. This is great. I'm going to keep it for my lab. I don't want to actually give it to anybody else. Or it could be that they make it open source, but they don't actually want to put any time into supporting it or into trying to find more users. If somebody wants to work with it, they can struggle through it. That's fine. But their feeling for their career and for their students is it's more important to work on papers, to use it as widely as possible, to keep developing it, as opposed to working on the sharing part. And then other people may have exactly the opposite answer, that this is a great thing. I can build my reputation on having hundreds of people writing papers on this rather than me writing 3 papers on this. And so it's the question of how do you make that decision? What do you base it on? Which I think gets back to lots of questions about incentives. And if you do make that decision, then that's where, to me, that somebody like an RSE comes in and they try to look at it and try to see. I mean, in some sense, you could say, like, where's the technical debt that you want to pay off? But that may be not exactly the right term here. But when do you put in these practices? When do you put in automated testing? When do you put in continuous integration? When do you start writing documentation more automatically? Kind of all those things. So I feel like that all kind of goes together when you make that decision, that it's no longer something that's just for you, but it's something that's going to be for other people. And in universities, I don't think we typically have the issue that you're describing in the NREL, where there's these things that are experiments that are intended, if they're successful, that are going to be used for lots of people, but we don't necessarily know yet.
Right.
I will say NREL also does have an RSE group,
Yeah.
which I don't know if you've talked with them or not. But, okay. Okay. Yeah.
And I'm interested in that too. So
Okay. Yeah. Yeah. Okay. Thank you.